So if we do not put an explicit contract size limit, it can easily create a denial of service attack vector. Uniswap developer, when they develop this smart contract, they already find this problem and then carefully organize their code, make sure they do not break this 24 kilobytes limits. I really enjoy to put a lot of different applications enabled by smart contract, but unfortunately, when compared to my Web2 developer experience, I found there's a lot of these limitations. Before doing that, I think it would be great if you have better grounds to test this in a more near production environment. I think this is something that I feel we can improve a lot of, like save our life kind of feeling. That's why I was super excited for this EIP.
Hello everyone and welcome back to PEEPanEIP, the series where we unpack Ethereum improvement proposals with the people who are shaping Ethereum's future. This is episode 152, brought to you by ECH Institute. I'm your host Pooja Ranjan and I'm joined by my colleagues Valeen and Akash. Today, we are diving deep into EIP-7907 meter contract code size and increase limit. This is a proposal that's particularly interesting for smart contract developers and protocol designs. We will explore the background, implication, and ongoing community conversation around contract size, gas metering, ext code copy, JUMPDEST analysis, and much more. And to walk us through it all, I'm excited to welcome one of the co-authors of this proposal, Zhou. For those who have recently started following us, Ki is a long-time contributor to Ethereum ecosystem. He has authored multiple impactful EIPs including 4804, 4972, 5018, 5027, and 5478. You may also remember him from our PEEPanEIP episode 106, where we discussed ERC 4804 Web3 URL to EVM call message translation. I'm truly excited to have him back on the show. Thanks for joining us here, Ki.
Hi, everybody. It's my great pleasure here to share our progress on EIP-7907.
I would love to kick things off with a quick introduction. So could you share a bit about yourself, your journey in Web3 and Ethereum ecosystem so the community can get to know you better?
Yeah, of course. I've been in the crypto space about more than 7 years. Before that, I was a software engineer, Facebook, Google, working on their large-scale infrastructure. So when I come to the crypto space, I found there's a lot of missing pieces in terms of infrastructure. And one of my favorite one is how to improve the EVM besides other, for example, scaling solutions like layer 1, layer 2, DA. That's why I put a lot of efforts about 4 or 5 years ago, wrote a couple of EIPs, try to improve different pieces of EVM in terms of, for example, the contract code size, and also a couple of others like addressing the stack to deep errors, and also how to deploy contract cheaply by using existing contract code hash. So I'm glad that this EIP is reaching for inclusion for next for Casa upgrade. So we'd love to share the details. I'm also planning on working on the Ether storage, which is Ethereum layer 2 scaling solution, which aims to provide long-term solutions for Ethereum block binding large objects that was introduced in EIP 4844, and also receive a lot of support from Ethereum ecosystem, including ESP grant.
Yeah. Thank you so much for the introduction. We really appreciate all your contribution in the ecosystem. I understand there are many more avenues and you are looking into two most of the important avenues, EVM and layer 2 solutions. So those are great to have. And in the process, you are also documenting proposals which can become Ethereum standards. So thank you so much for all the work you are putting in. Well, we understand we have a proposal to go over. So without further ado, let's peep in.
Yeah, sure. So this is today's outline. So first, I will give a brief overview of what is the motivation, why we want this EIP. And then I will dive into the details of EIP-7907. And then I will discuss some advanced topics, especially some of the topics are still highly debating in the Ethereum research R&D channel. So I will pick some of them and then would like to see if you are interested, and definitely would love to see your contribution. And lastly, I will summarize our work. So first of all, what's the motivation? So before EIP 170, that is the dependency of the EIP 7907, there's no limit of contract size. So contract is one of the, I think, the unique dynamic resources in the EVM. So other resources like, for example, OP code, like calculate summation, addition, or division, those can be easily evaluated according to their CPU usage, like it's just using constant resources. However, the contract size is a dynamic one. It can be very small, maybe 0 for most EOAs, and it can be super large. And at that time, there's no such limits. And processing this contract in both in terms of CPU, storage, memory is linear in terms of the contract size. Especially one of the most expensive resources is storage. So reading the contract from storage can be super expensive. So, however, Ethereum right now only charges constant gas cost, that is 2,600. So if we do not put an explicit contract size limit, it can easily create a deny of service attack vector. So here is my favorite part. So I will give an example. Suppose we deploy a lot of contracts with size 256 kilobytes. And then given the current block limit is about, gas limit is about 30 million. Right now, I think it's about 36 million, but right now I will choose this conservative number. And then an attacker can potentially create a transaction within the block that you take all the gas, that is the 30 million, and then read all those 256 contracts in a single transaction or multiple transaction using only 2,600 per core. So that will make a EVM client to read all this contract, which will take up to 2.6 gigabytes of data. Right now, our commodity PC, for example, SSD can only allow to offer about hundreds of megabytes of data reading sequentially. So which means that it will take a couple of seconds or maybe 10 seconds to read all this contract data. Suppose there's such kind of transaction that allow in the Ethereum network. While at the same time, we know that our consensus only have a really, really tight timing budget that we have to reach consensus of the block within 12 seconds. And the time for executing the block is even much smaller because we have to deal with other latencies, both in terms of block propagation, voting latency, or others. So which means that we can easily create a block that nobody can reach the consensus because it reads too much data. So that's why EIP 170, which was authored by Vitalik at the time, introduced the 24 kilobytes limit of a contract to avoid such DDoS attack. As a result, if we put this number into the previous calculation, then we can get the limit of the storage when a node reading from a block will be limited by 270 megabytes. And that can be easily processed in 1 or 2 seconds in a common commodity PC. And so this makes a lot of sense and also avoid this DDoS attack significantly. So that's motivation. So that EIP, I think, was about 10 years ago, was drafted in 10 years ago. However, with a recent rapid growth of the applications, especially like DAX, Uniswap, Curve, Lending, all kinds of applications. So the logic of contract is becoming more and more complicated. So unlike previously, we may have a very simple, for example, DAO governance or voting contract. Those right now we have really complicated logic. For example, for Curve, in order to perform the proper rate of swapped input token to output token, it actually performs some Newton iterative algorithm in their contract, which will be really complicated. And so which will create a lot of like large contracts. So a complicated contract can now easily exceed 24 kilobytes. I have experienced this for a couple of times, even like 3 or 4 years ago, and not to mention other popular dApp applications. So in order to avoid this to circumvent these limits, the one solution is how we can split the contract into multiple smaller contracts so that we are able to still perform this contract, but delegate part of these logics into smaller ones. Unfortunately, this means that when I first time wrote this contract, and then if I would like to deploy this contract, it may be different because I have to wrote contract first, make sure everything works correctly, test all these things. And then later when deploy, if I, oh, sorry, the contract is too large, then I have manually to split the contract, which increase the maintenance cost. Suppose now I have version 1 contract, and now I have version 2 or 3. It's really hard to work on like subcontracts, or if I still work on single contract, but every time I deploy, I have to split again. So it's really, really painful for a lot of developers. And in addition, because of this split process, it introduced a lot of complexity in order to deal with this, how to we are able to split these different logic into smart contracts so that they are like in one term we would like to be more modular to better to organize them, which means that it introduces a lot of complexity and create a lot of security concern. Suppose if I, for example, split contract, unfortunately the contract code is not the latest one, and which have some security issue. I'm sorry, the whole contract and the whole dApp is broken. So, and this is something that I personally has been experienced for a couple of years, and that's why I'm particularly interested in this problem, how we are able to solve the problem, not only for me, but also for everybody in the Ethereum ecosystem for all the developers. So here example, like how to split a contract. So originally we have multiple functions to behave. For example, I can do swap, I can get liquidity, I can add liquidity, I can get an estimate of the swap ratio, for example, for given an input token and what's the number of the expected output token. And since this contract is too large, we have to split into multiple subcontracts. And so, for example, these subcontracts put part of the logic into called subcontract 0. And in the main contract, that's we call subcontract 1, we'll call another function to another contract. Actually, this should be subcontract 0, function 2, so that we are able to still perform the logic while at the same time circumvent the 24 kilobytes contract limit. And so the one straightforward question is, why not we just remove these limits? Like this is kind of like a really small number, even compared to a lot of, I'm not say iPhone, but a lot of calculators. It's actually the processing power is much larger than 24 kilobytes. So in the EIP-7907, actually I previously contributed a small number of EIP, which has a similar idea. That's why I was invited to contribute to this EIP. And try to remove this one and impose a much larger, that's 10 times larger, that's 256 kilobytes contract limit. The reason we impose these limits rather than unlimited is because we found there's other constraint in the Ethereum protocol. For example, in the P2P network, when it send a contract to each another node, and it just send a whole contract in a single package to another node according to existing P2P protocol design. And unfortunately, the package size is limited. So if we send, suppose we are unlimited this smart contract. However, even though we are able to store this contract, we are not able to send this contract in the underlying networking protocol. So nobody can receive this contract. Suppose we have a super large size, for example, 1 megabytes or even more. That's why currently we still impose a limit, which we believe like 10 times is already significant to relieve a lot of developer burdens in terms of contract limits. So that's why we chose this number. And also, in order to reach this goal, we also need to carefully to satisfy some design constraints. So first of all, obviously, we need to avoid DDoS attack, especially with proper gas metering and implementation. Because I will show later, if the implementation is not correct, then we can still easily suffer from the DDoS attack. And second is that it should be compatible with existing deployed contracts, especially during this gas metering or repricing, all existing contracts should still work as before without any breaking issues. This used to happen before when we try to reprice some gas prices. We have to evaluate all existing contracts to make sure there's no breaking issues. So in the current design, we make sure that everything is fully compatible so that we do not require, for example, if some of the existing contract may be broken or ask them to deploy the contract. That is not go to us. So this is basic two constraints. So what is the basic idea? The basic idea is quite straightforward to introduce a called dynamic gas metering based on the contract size. So if the contract size is smaller than 24 kilobytes, then calling a contract of these smaller ones will take the same gas cost. That is still 2,600 gas for the calling the smaller ones. However, if the code size is greater than 24 kilobytes, so there's a key term how we can detect it's greater than. So I will explain it later, but idea is that once we detect it's greater than 24 kilobytes, then we will using called excess gas. That is additional gas that we are charged linear in terms of size so that we can use this gas to cover the cost of reading and processing these large contracts. So this is very straightforward, very simple, but you may have a question, why not we just implement this early? And why not we have choose this excess gas formula? And so I will explain later because there's a lot of tricky issues in terms of implementation and also a couple of other tricky issues in terms of the other costs, both in terms of, for example, paging cache and also jump analysis. And so since a lot of developers, they say, hey, they really like this EIP, they would like to have this solve this problem immediately. So the EIP-7907 is now chosen as the candidate for inclusion for the next upgrade. So there are a lot of work still ongoing, but we would love to see eventually it can be included in this upgrade to solve this long-term pain point in the Ethereum developing ecosystem. Okay, so first of all, how we address the DDoS attack. The general idea in Ethereum to address this issue is to charge gas before consuming resources. For example, I would like to take a taxi. The taxi will charge me a minimum rate no matter where distance it is. And then if my distance is too far away, then it will charge more. Suppose I go to airport, which is far away, it will charge more. But in Ethereum, since an attacker can put a minimum gas, that is the minimum money that when I take a taxi. So before I really move forward, I really would like to check the transaction or potentially attacker has already paid enough gas. So here is a pseudocode in the Ethereum EVM how to address this attack. For any steps, for example, for calling a contract, before do any resource expensive operations, for example, reading contract, do jump destination analysis, we will charge first the gas first, which is 2,600 as I explained before. And then after gas is charged, if there's no enough gas, then we will just reverse transaction and say, hey, there's an error out of gas error. And then we will read the account according to the contract address that the program provided, and then read the corresponding code according to the code hash that is stored in the account, which is an expensive operation because account is about 100 bytes data, but the code can be super large. As I explained, it can be, for example, 24 kilobytes, or it can be unlimited before EIP-170. So thanks to EIP-170, we can make sure that reading contract this operation is less than 24 kilobytes. So we can safely assume that this is being covered by 2,600 gas price that we previously charges. So we don't need to concern the DDoS attack, and then we can make sure the total number of the bytes that read from the code is just hundreds of megabytes using this charge gas first before consuming the resource. And however, if in the EIP-7907 cases, it is a little bit tricky. So on the right-hand side is a wrong implementation that supposed to implement this 7907 incorrectly. So we first charge 2,600 first, which is as before, read the account, which is the same before, and then read the code directly using the code hash. And this is something that can be broken if the code size can be greater than 24 kilobytes, because we undercharge the corresponding the expensive resources. It's just like take Uber, I only have $10, but I want to go to the airport, and then the driver did not check my balance. I don't get to the airport. I'm sorry that it costs $50, but I only have $10 to pay. So then this is definitely kind of an attack scenario. Even though we charge this gas later, but since this expensive operation happens before we charge this excess gas, so that will easily create an attack that can read gigabytes of data. Suppose we support 256 kilobytes contract limit. So the basic idea to try to solve this problem is to have a way to know the contract size or know whether the contract is a large one and its corresponding size. So here is one of the implementation that we are proposing. Actually, there are three different types of implementation try to address this problem. So the first here I introduced perhaps the simplest one, which is that we have additional index tells what is the code size of the corresponding code hash. And then so that we read this data first, because the size data is much, much smaller, in general, less than 3 or 4 bytes, so that we can still use the 2,600 gas to cover this cost. And then once we have this information, we can calculate the excess gas and according to our formula, and then charge the actual excess gas before we really read this contract. And this is a really simple idea to solve this problem, quite straightforward, but we will see that there's different concerns because actually you can notice that we have doing additional small IOs here that is read this contract code size compared to the left-hand side implementation. And also, we need to implement this data structure for existing clients. So this will take extra efforts for existing client to upgrade their database schema to support this indexing. Even though this is viable solution, but this definitely complicates some of the implementation of existing clients. So this is basically all of the details or procedural how we implement EIP-7907. But now I would like to dive into advanced topics when we implemented 7907 and also a lot of discussions with co-developer to see other problems. So one is the code warm state for the code itself. So in Ethereum, they introduced the code warm state, kind of like cache mechanism in EIP-7929. And unfortunately, there is missing the corresponding state for code. So we are also going to introduce that in this EIP. And another question that I also already mentioned is how we are able to implement efficiently to read the code size. Is there any other approaches? So here I will give another 2 implementations. And also we have done a lot of analysis on other causes that may be impact to the performance of the EVM, both in terms of jump destination analysis and also when we have large contracts, suppose the contract will have the code that to try to invalidate, evict the cache, page cache or L1, L2 cache because the contract can be super large, then what is the performance impact? So there's some topics that we found, and there's also a couple of other topics like how to choose the exact gas function or ext code size. Probably we can answer this later. So EIP 2929 introduced a code warm state, which means that, for example, when the first time I call a contract, we will use 2,600. However, when the second time when I call a contract on the right-hand side, it will only use 100. The reason is that when I call the contract the second time, the account and its code is already warm or already in the cache. So when I call it second time, I basically just read the data from the memory. and there's no expensive storage read. And that's why we do not need to charge 2,600 and we just charge a minimum 100 gas in order to cover the corresponding memory cost. So this is really, really helpful for a lot of developing smart contract, especially they observe when they call a contract, some contract frequently, their gas price is significantly reduced because of this cache mechanism. Unfortunately, this cache mechanism only applies to two objects in the Ethereum state system. One is the account. So this is we can see this read account. And second is the storage slots. For example, when I read the USDT balance again and then read a second again, then it will only charge 100 gas for the second time reading. Unfortunately, the code itself is also a special object and take a considerable cost in terms of storage. So right now we miss this code warm state for the code. And so that's why we explicitly added this code warm state for code in EIP 7907. So suppose in the same transaction, if we call a contract, maybe this contract can be super large, maybe 256 kilobytes. The first time we will fully charge this contract using our formula that's 2,600 plus the excess cost. But for the second time, when we call the contract, and if we detect this code is warm, then we are able to basically access this 256 kilobytes of the code in just 100 gas cost. And this will be greatly useful for example, calling a large contract frequently in a single transaction. And one thing we notice is that in EIP 2930, there's called transaction level access list, which allows to pre-warm corresponding objects, that is account and storage slots, before execute this transaction. That's just after 2929. So it's called transaction level access list. So unfortunately, since we would like to change the EIP or made further improvement on EIP 2930, which will introduce a new transaction type, the contract code or warm state will not be able to pre-warm by the previous EIP 2930. That is some future topic that we can cover in the future EIP. So another issues that we have been discussed a lot recently in the Discord channel is to how we are able to read the code size efficiently. So there are a couple of concerns of using an index of code hash to code size. So first of all, I have to update the current database schema. So for example, all the existing, suppose I have a node that already running with a lot of old contracts. Now I would like to upgrade the node to support this large contract, which means that we have to upgrade existing database with existing data. We need some technology called backfilling, which basic idea is to have a backup thread, a background thread that is scanning all the old contracts and try to write this index. And definitely create some additional complexity to implement this feature. And also it requires actual DB lookup so that we can charge excess gas before we read the code from the database. So this create a little bit extra latency compared to previous implementation. So we have two methods to try to read this code size efficiently. So first method is to reuse a lot of database features. So most of databases actually already knows the value size. The value size, that is the code size before we actually reading it. But unfortunately, I think this is a really, really special case for our blockchain because we want to know how many resources, how many data we want to read before actually reading it. But there's a really, really few use case for existing database. So most of them, or all of them, to our knowledge, did not have this API, public API, to tell what is the size of the value of a key. The key is the code hash. So in order to support that, you may have to either create a fork of this database to expose this API or ask them to say, hey, whether you can expose these APIs to the public. So this may take extra time or maybe extra maintenance effort. So, but we would love to see how the database also can be involved to support the different applications, especially blockchain applications. There's another method. Here is the second method we call large contract detection. It is a little bit complicated, but the basic idea is try to reuse existing data schema. But when the code is greater than 24 kilobytes, then we write the existing code hash to code schema with the first 24 kilobytes plus additional information that is the number of bytes of the code. So this actually I should probably highlight this part. So this is the when writing this part, how we write a special code so that we can allow when reading a contract, we can detect, oh, this is a really large contract and this is the size, but without introducing additional indexing or additional DB reading, but just read two data. Where first data is the first 24 kilobytes of data plus the metadata of the code size, and then read the rest of the code and put it together to obtain the full code. So this is another solutions. And one question of this solution is that whether there exists a code before EIP 170 that has a contract that with greater than 24 kilobytes. Otherwise, the whole assumption will be broken because we assume all the contract is smaller than 24 kilobytes. And thanks to the community developers in the Discord channel, we basically iterate all the contracts, existing contract, and found all of them is less than 24 kilobytes. So which means that we can use this way to have call to detect whether a contract is a large one or not. And another topic is called jump destination analysis. So what is jump destination analysis? It's basically to find all the valid or invalid jump destination of contract. So that this is a safe feature of Ethereum virtual machine, which is able to, when I jump, so for example, I go to another instructions that is to another arbitrary location of the code, we want to avoid this jump to we call the data section of the code. We want to make sure it's called to a really code section of the code, because the code consists in the EVM, the code is mix of the code section and also the data section. So if we jump to the data section of the code, it will become invalid and then it will be automatically reverted because it cannot pass the jump destination analysis. And so this issue should be addressed by UF, which we separate the code and then the data section so that we can have a more clear jump destination analysis. But right now in the Ethereum, we have to scan all the code in order to figure out which locations are valid or not. So thanks to Charles Cooper, he is also the author of the EIP-7907. He has done a benchmark to evaluate the performance of the jump analysis for very large contract. For example, it can be, right now, the example on the right-hand side, it can be up to 15 megabytes. So the result on the right-hand side shows that actually you can check the fourth column, which shows the processing rate of per kilobytes, which we observe that when the contract size is reaching some large number, because we can reach some constant number, it's a stable number if the size is large enough, then we see that actually the size, the processing time per kilobytes is constant, which means that the cost is linear in terms of size. So which means that as long as we are able to charge the core in using the linear size equation, for example, in the current excess equation, then we should be able to cover the corresponding jump destination analysis cost in our benchmark. So I think this is a really great result, and we'd love to encourage you to deeper look at how the benchmark is being done and how to obtain these numbers. So the last one topic I would like to discuss is how the large contract may make impact to the caching. This include page cache, include L1, L2 cache. Basically, the worst case scenario we want to investigate is to see if we have a contract that have a pure long jumps of different locations of code, so that you will try to evict the cache and then create additional cache cost in terms of when we call in the contract compared to smaller ones. Because the small contract, we can put them mostly into the cache, so we don't have this concern. But when this code is large or super large, then the cache effect will kick in. we key in, and then it made her the performance. So on the right-hand side is a very simple assembly code that I wrote to create a contract with just purely random jumps. And then we run this contract, simulate the execution of the contract on some commodity PC, including my MacBook and also Intel x86 machines. The early result shows there's only 1% difference, mainly because right now commodity PC has very large cache, like for example L2, L3 sometimes have a couple of megabytes or tens of megabytes. So it's still able to fit the whole contract code into their cache like a layered cache. However, if you would like to run the contract with smaller caches on some weaker devices, um, that may create significant different numbers. But unfortunately, I don't have these devices, so I'm asking more community help to figure out the performance difference there. So that's pretty much all I would like to share in today's talk. There's a lot of references here. I would love to encourage you to visit live discussion in Ethereum R&D is still actively discussed in the Ethereum R&D, especially some like topic I just mentioned. And there's also we also have a prototype in gas and execution spec. And then so that it basically kind of like you can compare with my pseudo which I showed before. And then you can also take a look at our benchmarking and then try to play some of them to see what's the difference there. So many thanks for inviting me to the talk, and also would like to thanks a lot of people, including Charles Cooper, and then to make everything happen for the EIP 7907. So, yeah, love to see how that eventually can be included in the next Ethereum upgrade. Yeah, thank you.
Thank you so much, Key, for explaining all these. This EIP is substantially increasing the hard contract code size limit from 24 KB to like almost 10 times or a little over 10 times. For people who aren't aware, this proposal was recently documented. It was documented in March 2025. And this is a standard tracks core proposal. So definitely we need to see this proposal in some kind of upgrade, and we are happy to share that it has been selected for considered for inclusion. So many congratulations to you and the co-authors to getting this proposal so far.
Thank you.
You have mostly answered questions that I was having on my list, but I would like to get clarity on a couple of more things if someone may have missed it in the presentation. So my first question to you is with respect to the gas per word. So why was 2 gas per word selected? And is it the same constant that init code word cost from EIP 3860?
Yes, that's the idea that's proposed by Charles Cooper. And so I believe the basic idea is the same as the try to adjust the init code. So that is almost the same. Actually, or was also proposed, not documented, but in the discussion to use a more conservative number, which is so the excess gas will be the number of the 24 kilobytes of data that read. So round out number of the data that is per 24 kilobytes and times 2,600. That's another number that was proposed in the old standard. The basic idea is to see, hey, suppose I read a contract with, for example, 40K kilobytes, then I will charge the twice of previous 2,600. And that's another excess gas parameter that I would like to probably better compatible with the existing contract calls. So suppose I have 24 kilobytes in a big contract, then I just charge 3 times of 2,600. So that's the number that we choose. Still, this is not finalized yet, so we still there's a lot of discussion how to validate this equation and whether we needed more benchmark. But I think the basic idea is how we are able to make the cost is linear in terms of size.
I understand when a proposal is CFI'd, then it means it would be selected for one of the devnets that is proposed for the network upgrade. So do you think the devnet testing could help you get finalization on the number that is selected here?
So I think Devnet definitely can help. But before that, I think we would like to investigate all the worst case scenarios because even for Devnet, nobody like there's very few people try to attack Devnet these days, right? So it will be really to see whether it works properly with other components, for example, the Dev P2P or those components that we haven't been covered in our design. But a lot of worst case scenarios, for example, jump destination analysis and also caching, all these things will be easier to discover by our benchmarks. So yeah, we would love to see that may discover more problems than our expectations. So yeah, the earlier the problem discovered, then the less cost we would like to make it happen in the mainnet.
Yeah, and I noticed in your list of thank you was Marius. Marius is one of those people who love to like spam and go for more and more testing on DevNet. So we hope that this will be tested and we could get the final number over there.
Yeah, sure.
Well, I notice at present the reference implementation in the EIP is pretty empty. However, I have also noticed that in your presentation where there pseudocodes. I'm just wondering, is there any consideration of adding these pseudocodes as reference implementation in the EIP?
Oh, that's a good question. So the thing is like we haven't added this reference implementation is that the exact implementation of how to read the code size should not be like restrained by our reference like implementation in EIP. So EIP is more instructions, say, hey, this is how we can do. We can list different types of implementation to read the code size. But we shouldn't say, hey, this is the only way you implement a client. Any client can choose the way they would like to prefer to read the code size. So that's why I think if you check I think I list the execution spec, this one here, I think this is really, really excellent pseudo-code written in Python, much better than I would say my pseudo-code. My pseudo-code is probably the minimum pseudo-code, but it's not able to functional. So this is perhaps most functional execution spec, which give you very simple, elegant way how we are able to put into execution spec and almost runnable in the Python language. And also we have a Go Ethereum implementation and other client implementation should become quickly, but it should not be that difficult so that for other clients, they can take a look and see how it works. And then yeah, definitely if people are asking, say, hey, we need more information in the standard, then we can include it. But yeah, that's the current state. We don't want to like say, hey, this is the actual implementation. So we also discussed questions, these concerns with Charles Cooper, and then our conclusions, and we do not change the standard at the moment.
That sounds good. I pointed it out because we have noticed sometimes like it still remains in to-dos while we do some kind of like testing and reference implementation is documented somewhere else but not in the proposal. So just a reminder, maybe before moving the proposal into review status, if you would like to add the execution specs link over here that can help other clients implement it would be nice to have.
Yeah, that's great. Yeah.
Very well, in the presentation discussed about some of the trade-offs, like trade-offs with respect to 2930 is already explained. Some limitations, concerns using index are also there. I'm trying to understand if there are any more trade-offs that you would like to share with the community or the smart contract developers should be aware of.
So another trade-off that actually I'm also working with the Charles Cooper is regarding the memory size limit of the Ethereum. So for example, in Ethereum, when we deploy a large contract, we first have to prepare all the code in the memory and then return this data to the EVM to tell what is the actual contract we want to deploy. So suppose the contract right now is 256 kilobytes, which is our limit. It also takes considerable memory cost because the Ethereum memory cost is a quadratic, which is the memory cost is quadratic in terms of the memory size. So when we deploy a large contract, the developer may found even though the cost, we break this limit, cost is expected in terms of deployment cost, but the actual cost may be higher because it consumes more memory, which is also out of the original design of Ethereum. So that's why we are proposing another EIP try to solve this memory limited problem. Actually, Vitaly also noticed this problem and try to replace these quadratic terms, we're also using just pure linear terms. But definitely, there's also a lot of things that need to investigate in both in terms of performance. For example, as I explained, suppose we have super large memory, which can be a couple of megabytes or maybe tens of megabytes, which we can allocate. And then this caching mechanism, all those things also create additional concern in the full analysis. So yeah, we also have been done a lot of benchmark, but I'm not sure that EIP will be included in the FUCASA maybe in the future because we don't want to take the full plate at the first time. Just like make sure we address the most painful problem one by one.
I really hope, keeping my fingers crossed, it should get included. Whatever issues or challenges we may have should be under control. And if it is found in Devnet, that would be nice to have.
Yeah.
Well, if you have to suggest, what kind of applications do you think that will stand to benefit the most with this proposal?
I feel a lot of smart contracts, especially complicated ones, will be benefit from this EIP. I can name a few. For example, when I try to deploy Uniswap v3 and try to add some features by myself, and then I can easily hit the contract code size is great its limits because I believe when the Uniswap developer, when they develop this smart contract, they already found this problem and then carefully organize their code to make sure they do not break this 24 kilobytes limits. For example, they separate part of the mathematics library out of the contract and do the similar trick as I explained, split contracts into smaller pieces. So with these upgrades, I think all the developers, when they try to, for example, deploy or reuse existing contract, try to improve on top of that, can be easily done without carefully reorganize the code and maintains this code. So in general, as long as your contract is a little bit complicated, I believe, then you can see the difference before and after this EIP.
Very well. My next question is with respect to one of the most popular EIPs that was included in the Pectra upgrade, EIP-7702.
Yes.
Would you say that this EIP in any way relate with EIP-7702's delegate execution model? Like if it does, will it benefit user or implementer of this proposal?
Yeah, so we carefully examine all how the code being implemented in 7702. One thing is notice that for 7702 is able to upgrade EOF to smart contract based EOA. And then, but the code that write to the contract, write to the EOA is very small. That is, I believe, the prefix that is, I think, 4 bytes or 8 bytes, and then plus the address to 20 bytes. So in general, it does not break any assumption 24 kilobytes, greater than 24 kilobytes assumption in our design. But there's a couple of things, for example, when a contract started, and then it will try to authorize a list of the code to delegate to another code. And we found there's a couple of attacking vectors because this authorization, and then they may authorize delegate to reference to large contract, and if without proper gas metering, it can be easily be attacked. Basically, any pieces of the code that try to read the contract code in the client, we have to carefully investigate to see whether it's properly charged before we really read the code. So there's a couple of the details implementation. Actually, all of them has been addressed in the prototype. And so at this moment, we have examined all the reference of the reading code contract and then make sure they're properly charged and then properly put in the prototype. So yeah, we are pretty in high confidence that there's no such kind of concern introduced by EIP 7702. Yeah.
That sounds quite comforting. And my next and perhaps the last question with respect to this EIP is about the other contracts which are already existing. Is this proposal backward compatible, or how do you think it is going to affect already existing contracts?
Yeah, it's fully backward compatible. So all the existing contract will be the same, using the same gas cost and using the same, for example, reduce the gas cost using the warm cold state. So everything, we do not break any existing contract. So yeah, everything will be work as usual.
That's very good to know. And perhaps this could be one of the reasons that despite being an EVM proposal, it is being considered for inclusion in the upcoming network upgrade. Well, thank you so much, Key, for sharing a lot of information about EIP 7907. I would like to quickly take a few moments to talk to you about some related but interesting aspects of you as a person that would help our community to know you better. This is called as rapid fire round. We try to collect information or response in one word, one sentence, or very few sentences you can use just to respond to some of the questions. Would you be open to that?
Yeah, of course.
Very well. My first question is one EIP you are most excited about it right now?
So I think this EIP 7907 definitely is most exciting about. Actually, this is not the first EIP I try to address problem. I actually have drafted a previous EIP. I forgot the number, but it's starting from 4 or 5. You can imagine according to the number that's a couple of years ago to address this problem. Because also a contract developer, I have to roll a lot of contracts. I really love the idea of the contract, and I really enjoy to put a lot of different applications enabled by smart contract. But unfortunately, when compared to my Web2 developer experience, I found there's a lot of these limitations, both in terms of contract size and also memory size. So I think this is something that I feel we can improve a lot of, like save our life kind of feeling. That's why I was super excited for this EIP. And definitely I have another more precisely, it's not EIP, ERC, that's for 4804. And they try to convert the Ethereum into a decentralized, unstoppable HTTP server. And that's a really interesting idea that I'm still exploring for. And so we'd love to see how we actually enable a lot of new applications on top of Ethereum.
You have authored multiple EIPs, and in general, it happens in the ecosystem that not all drafts reaches to the final status. So, if there is an EIP for which you would have wished that it got adopted but it didn't, what that EIP would be?
I think a couple of the EIPs, but one of the like EOF, I think this is a really interesting idea how to make the code format and better organized. For example, I just mentioned the jump at destination analysis. It can be completely eliminated by the EOF, but since it has really radical changes of underlying format, so I imagine that still take a lot of time to make it to mature. So before doing that, I think it would be great if you have better ground to test this in a more near production environment. So yeah, but that's something that I would love to see how we are able to speed up this EIP process. Yeah.
Very well. EOF is definitely out of Osaka, but we can consider it for Glamsterdam. So we'll see how it turns out to be. And talking about EIP process, what would you say is your favorite part of the EIP process?
Yeah, I think the EIP process, so it's really everything is open. Everybody really love to especially discuss the how to make sure the EIP from different aspects. Especially I through this process, I know a lot of friends. I also learn a lot of things that I previously probably oversimplified how to make a EIP to become a mainnet, especially for example, previously I haven't done too much benchmark in terms of caching and also jump destination analysis, and especially how this work for the existing code, how other people has been done to support this. Because when we just read the go the Ethereum code or when we read the Ethereum spec, there's a huge, it's like iceberg. So there are the eyes on the top, which everybody can take a look at how it works. But there's a lot of underlying why we do this, what are the concerns, what are the other considerations, because designing EIP is a systematic work. It's not just smaller pieces that are like in Web3 system that we can fast iterate a version every day and deploy. And if something is wrong, then we can roll back. No, this is not the case in Web3. We have to make sure everything is correct. So there's a lot of tooling, benchmark, all those discussion information that flying around. So especially from outsider perspective, I have met a lot of different people that not familiar with EIP when they discuss, oh, if you should do this, should do that. I say, hey, do you know that there's a lot of considerations when you implement EIP? Do you know that you have to use these tools to test, benchmark, all those things? So I think it would be great we have a way to have more tell people the underlying the iceberg, how it looks like. And then so that people can better understand how they are able to contribute to the ecosystem, because like the simple wording is effortless, right? But there's a lot of things that happen under the hood. So yeah.
Right. And if you have to say like one of the hardest challenge in moving the EIP forward, what that would be?
I think it's still the how to make sure like everybody has different concerns. So how to make sure everybody is be able to align on the same page. So they have concerns of the memory, they have concern of caching, they have concern of the storage, they have concern of the upgrading database schema. So addressing all these concerns, and different clients may have different concerns because they had implemented ways in differently. They may have different databases, they may have different database schema. So aligning all people together on the same page, I think is most difficult part. But the good thing is like, so everybody is really willing to contribute this. Everybody admit that this is a problem. We have to solve it. No matter it's 256 kilobytes or maybe smaller, maybe 64 kilobytes. We definitely would have to should solve this problem. So I think as long as people have the same goal, people gradually discuss all the things in a logical way by filling the information that everybody is missing. I especially love the discuss channel in the R&D. People at the beginning have a lot of, you can clearly notice that people may have different pieces of information, but jointly together, people gradually align with the how this is the how we can achieve this goal, and people agree with each other, so that you can imagine this is a really good joint work with all these people, which I name in the acknowledgement. Not just my single like contribution. So I really enjoy this process with the joint efforts from everybody here.
Herding the developers can be challenging sometimes.
Yeah, yeah.
Very well. A founder or a builder in Web3 space that you admire the most?
Oh yeah, I think definitely Vitalik is the person. Actually, I work with him, like some small grants and like for example cross layer 2 bridge, and then also discuss with him some different topics, for example the storage or memory or these things. So I think I really admire that he's really open-minded. So you can freely to talk with him no matter online or offline. And then sometimes I also feel he is overwhelmed by a lot of different signals, or sometimes maybe a lot of noises, but still he would like to listen to what the community, the voice from the communities. And sometimes I feel like if I commit into that position, it will be with a lot of pressure because I have to deal with a lot of this informations, and sometimes I feel like, oh, that's too much burden for like from my understanding. So I think she is doing pretty well, and definitely I think Ethereum it should not be ecosystem should not be a single point failure. Then we should have more people that work together. So for example, in this EIP, I don't think there's not too much contribution. Vitali is aware of this, but I personally like talk with him about this direction. He said, yeah, this is something that really should make it happen. So for example, made 128 kilobyte size or something like that. So he is aware of everything, but not necessarily joining all the details. Trusting everybody in these experts can address all this problem. Yeah.
That's great. Yes, he is a great inspiration in the ecosystem and he's definitely open to talk. He has been kind enough to show himself on PEEPanEIP and explain the proposal that he wants to share for the ecosystem betterment. So we are so grateful to his work here.
Yeah.
Well, Key, that was incredible, insightful. Thank you so much for walking us through the motivation, mechanics, and the trade-offs of this proposal. We hope that this proposal goes into the Fusaka upgrade. It's already in CFI, but we hope to see it's getting promoted and getting into schedule for inclusion soon. Thank you for joining us here today.
It's my great pleasure.
Dear listeners, if you would like to dive deeper into this proposal, you'll find the links in the show notes to the full EIP community discussion thread and other supporting resources. As usual, if you care about Ethereum's governance, protocol evolution, consider sharing this episode. You can also support the public good works that is being done with Ethereum cat herders by donating them at eatcatherders.com/donate. Until next time, keep reading these EIPs, keep building good products, and stay curious. Thank you for joining us here today.